Alright, so I want to look at a video on finding the volumes of solids generated by revolving regions around certain lines. And this video we're going to be looking at the disk method and the washer method. Okay, so disk, which is just going to look like a circle, and the washer method. Okay, now a washer is going to look like a circle within a circle. Okay. So when we're doing this out and we're using disk method, we're actually going to be taking the area of the entire circle here, that entire inside. And you know that area of a circle is pi r squared. Okay, where the distance from here out to our circle is r. Now for a washer, the area that we're going to be dealing with is going to be in between here. So it's going to be this area right here. And the way we're going to find this shaded area for my washer is simply by taking the large radius, okay, and doing the area of the circle with the large radius. We'll call this big R. So the area is going to be that pi r squared. And we're going to subtract out our little area of our circle here, which we'll call this a lowercase r. So we're going to minus off the area of that smaller circle. Because if we take the big area minus the smaller area, that's going to leave us with just that shaded blue region there. Now this is the idea that we're going to be working with these problems. So let's go ahead and take a look at an actual example here. So for number 1, we want to have the line y equals e to the x minus 1, y equals 0, x equals 1, and x equals 3. We're going to revolve that about the line y equals 0. Okay, you know what? First things first, we should probably graph this. So let's graph e to the x minus 1, which should just be e to the x shifted 1 over. But you know what? I want a nice graph, so let's make a nice graph here. So we have y equals e to the x minus 1. So if I graph that here, okay, that's not what that's supposed to look like. E x minus 1 is not a straight line. Hold on. You know what? I guess we'll have to do it with the calculator then. Okay, so we'll go y equals e to the x minus 1. Okay, so it should look just like that. Perfect. All right. So again, you could see it. It's just shifted 1 over to the right. It's that normal e to the x curve shifted 1 over to the right. You know what? I'll just actually draw the graph here. Right, so let's say here's my graph. And what this is going to look like is it's going to look something like this, where right here, this is 1, 1, that point. Okay, and this is our graph y equals e to the x minus 1. So this is going to be, and we're going to bound it by y equals 0, which is just the x-axis here. So that's y equals 0. We're bounding it by the line x equals 1. Okay, here's the line x equals 1. And we're doing x equals 3. Okay, and here's x equals 3. Okay, so this is x equals 1 and x equals 3. All right, so the region that we're going to be rotating here, okay, to figure out the volume of, is this region that's bounded by all of those lines. Okay. So, how are we going to do this? First off, we need to determine, is it going to be the disk method or is it going to be the washer method? Well, this one is just going to simply be a straight disk problem because our radius here, now when you're drawing these out, let me explain this a little bit better here. Your center line should always be the line you're revolving around. So the line y equals 0 is where I'm going to go to. I'm going to just put a dot. And I'm going to drag this up until it hits that top line. Okay. Because that line is what's getting revolved around here. And you could see this kind of circular shape that's being formed. So there's my r, my radius there. Okay, and when you're looking at this region is just composed of a bunch of circles. Like if I took this here and I said, okay, well, this is like the same thing here. This is another circle that's being revolved around here. And all we're doing is we're stacking those circles on top of each other. Okay, but you'll notice like this circle on the right here, that looks a lot bigger than the circle that's on the left of it. So how do we account for all these circles? Well, we put the radius in terms of the function. So what we're doing here is we're going to go ahead and use that area formula. Remember, we said the area of a circle is pi r squared. Well, we're going to bring in an integral so that we get the area under the curve here, and we're going to do pi r squared. Okay, but what we're doing is, since we're revolving this around the line y equals 0, we want everything to be in terms of x. So we're going from x is 1 to x is 3, and then our radius here, r, is the distance from 0 up to this line. Well, that's the y value of my function. That radius is the y value. This radius is the y value of the function. The total height at that one is the y value. And we know y is e to the x minus 1. So this becomes e to the x minus 1 dx. So that's going to be what we're going to be integrating here. And we're taking that whole thing, the radius squared. Okay, so that's our setup, and then we just have to go ahead and evaluate that. And I just want to kind of draw this in just so you see this. Okay, when we are doing the area all this around, okay, you can see we're taking the area of this entire circle because integral gives us the area under the curve. We're taking that area, then we're taking the area of this circle as well, and all the circles from 1 to 3 stacked up. And that's how we're getting the volume, because what we're really doing is we're taking the area of the base, or the area of some shape, and multiplying it by the height, or the stacked up version of all of them together, and that's what the integral is doing here. Okay, so then we can go ahead and evaluate this. Now, I don't know if this problem, if they were meant for you to evaluate it by hand or not. I'm not 100% sure, so I'm just going to evaluate it by hand just to be safe. Okay, so this becomes pi integral 1 to 3. And e to the x minus 1 squared is like e to the x minus 1 times e to the x minus 1 dx. And remember, when you are multiplying exponents with common bases, we add the exponents together. So this is basically the same thing as saying e to the 2x minus 2 dx. Okay. And so now we have to integrate that. So I'm going to bring in a u substitution here to do this. So I'm going to let u be 2x minus 2. And then du is going to just be 2 dx. All right. Well, I'm missing a 2 in here, so I have to put a 2 in here, which means I have to put the 1/2 out in front. So I can rewrite this as 1/2 pi, and I'm going to leave off the integral things because I don't want to convert those as well. And then this is e to the u, and then 2 dx, well, that's the same thing as du. So then this becomes 1/2 pi, and then the integral of e to the u is just e to the u. Okay, well, now I'm just going to put my u back in here. So we have 1/2, this is pi e to the u, which was 2x minus 2. And we're going to integrate that now. We're going to put back in our 1 and 3. So if I finish this out here, we get that this is going to be 1/2 pi. And then we have e to the 2 times 3 is 6. 6 minus 2 is 4. And then minus 1/2 pi e to the 2 times 1 is 2. 2 minus 2 is 0. E to the 0, which is just 1. So our final answer here we get is 1/2 pi e to the 4th minus 1/2 pi. You could also factor out the 1/2 pi, and then you'd have e to the 4th minus 1. All right.